Good afternoon. My name is Emily Shoemaker, and you will also be hearing from Jordan Pelegrin and Myah Rhines. Today, we will be discussing the groundbreaking advancements that have been made in the field of prosthetics that have allowed for sensory motor function and touch sensation.
Prosthetics are assistive devices used by people with amputations to help them increase functional activity. Prosthetics can be on your upper limb or lower limb. Types of prosthetics are body-powered, myoelectric, computerized, and bionic. Pictured here is a bionic arm. Prosthetics do have some problems. They can be not cosmetically pleasing, which causes a lot of people not to get prosthetics. They can also be uncomfortable with the socket, which can cause a lot of stump pain, blistering, or bruising. And they can also be not functional, meaning they might not be weight bearing. Prosthetics also don't have a sense of touch, which we will discuss in this presentation.
So how exactly do we restore the sense of touch in prosthetics? Well, in 2013, a team of researchers at the University of Chicago sought to answer this question and focused on two main components. Number one being the motor signals that the brain sends to the body part, and number two being the sensory signals that the body part sends to the brain. Their first set of experiments focused on sensing where the skin had been touched. Animals were taught several patterns of touch with their fingers, and then electrodes were connected to areas of the brain corresponding to each finger. The physical touches were replaced with electrical stimuli, and the results showed that the animals responded the exact same way to electrical stimulation as they did to physical touch. The second set of experiments was dedicated to investigating the sensation of pressure. Researchers developed an algorithm that was able to determine the amount of electrical current needed to generate the sensation of pressure. The results of these experiments also showed that animals responded the exact same whether the stimuli were felt through their fingers or through artificial means. The last set of experiments was dedicated to investigating the sensation of contact events. When a body part first contacts an object, it produces a spike of activity in the brain. The results maintain the concept that these bursts of brain activity can be mimicked effectively through electrical stimulation.
So how does one use these prosthetics? As most technology does, these prosthetics range in various concepts and strategies. To start, the Luke arm has been in development for 15 years. And how it works is through tapping into the wearer's nerves to send signals back to the brain, mimicking a sense of human touch. The arm works through an array of microelectrodes called the Utah Slanted Electrode Array, implanted in the wearer's forearm and connected to a computer, allowing communication between the prosthetic arm and the brain. Through the touch sensors, the artificial hand then sends computer-generated touch signals back to the brain and also interprets signals from the remaining nerves in the arm, which is actually able to detect temperature and pain. The next type of prosthetic is the electronic skin, or eDermis, which was shown in the previous video. Engineers at Johns Hopkins University created this electronic skin, which when added to a prosthetic hand allows users to feel objects as if it were their own. The skin is electronically connected to nerves in the arm that are involved in relaying the sensations of touch and pain to the brain. Lastly, PhD assistant professor of neuroengineering at the Swiss Institute of Technology created a sensor-studded insole, which is placed beneath a prosthetic foot. This can be added to a wide range of prosthetic models. And to link the insole to the residual nerve network, researchers developed an interface or a wireless system controller to capture pressure information from the insole. They also worked with a prosthesis manufacturer to encode data from already existing sensors in the knee of a prosthesis and sent that to the system controller as well. So as I explained in the previous slide, there are 3 types of devices that we looked at and analyzed. With the Luke arm shown on the top right of this slide, Chloe Kent from the Medical Device Network says test subject Kevin Walgamot, whose arm was amputated below the elbow after an accident 17 years ago, can now use this prosthesis to feel 119 different touch sensations. For example, he can distinguish between large, small, soft, and hard objects, and is able to handle delicate items like eggs and grapes. For the eDermis, or electronic skin, shown on the left side of this slide, this was designed to fit over prosthetic devices that are already in use by individuals. This will allow the wearer to tell the shape of what he or she is picking up, and sharp objects will actually cause the feeling of pain, which is an attempt to give a person a range of realistic sensations. This could also help avoid picking up something that's sharp that could damage the prosthetic. Lastly, as shown in the picture on the bottom right of this slide, the sensor-studded insole. Lab and clinical tests of this system for the sensor-studded insole showed that the sensory-enabled system provided such enhanced sensation from the prosthetic foot and knee that patients experienced greatly diminished or eliminated phantom pain, and better mobility, including much improved walking and even challenging situations such as stairs or deep sand and over obstacles.
As evidenced in this presentation, there is a wide variety of new technological advancements in the field of prosthetics. There are millions of Americans that suffer from limb loss, and the up-and-coming research presented offers the possibility to return this sensation of touch to millions of people. Now that you've learned a little bit more about the recent technological advancements in prosthetics, we have 2 important questions for you. First, as more research is conducted, new prosthetic technologies inch closer and closer to entering human clinical trials. What implications would there be if this new prosthetic technology became readily available to everyone? Secondly, once this new technology becomes available for widespread use, there will be problems with cost, distribution, access, etc. How would you devise a plan in order to minimize problems with implementation? Thank you.
Thank you.
Thank you.